today we will first look at a practical, well, not really practical, but we will see at the computer an application of the SVD, singular value decomposition technique of yesterday. And then I will propose one or two exercises about it. So, just to remember what we have said yesterday. The idea of singular value decomposition is that every matrix X can be represented as the product of three matrices where let me just repeat. So if X is an n by m matrix, using the notation so that m is the number of, for example, documents in our repository, and n is the number of coordinates in the df by df space. So, of course, U is going to have the same number of rows of the matrix and a number of columns equal to the rank R of the matrix. So we define R as the rank of matrix X. This is U. Sigma is an R by R diagonal matrix with positive values, and we will assume that everything has been permuted so that the values in the diagonal are in decreasing order. And finally, V, actually V transpose, the last matrix, will have, of course, the same number of columns as X and R rows. So, of course, what I have just said does not define uniquely this. Additionally, U and V are column orthonormal. And a simple way to define column orthonormality is to say that U transpose U is the identity matrix, and also V transpose V is the identity matrix. Okay, so the dot product of two columns of U is 0 if the two columns are different, and 1 if they are the same column, and so on. And so we can write sigma as the diagonal matrix with values sigma 1 down to sigma R, where sigma 1 is greater or equal to sigma 2, and so on, until sigma R, which is greater or equal than 0. Well, moreover, actually, if R is the rank of the matrix, it means that there are no 0 values. So if R is the rank, sigma R will be strictly greater than 0. These conditions together define the singular value decomposition of the matrix. In particular, the sigma values are called singular values. I've shown you yesterday that this is sort of generalization of eigenvalue decomposition, at least for the generalization of the eigenvalue decomposition for symmetric and positive definite matrices. And finally, the main application of this is, okay, suppose that we have a new document, Q. A new document might as well be a query in our search engine. So it's something that sits in Rn, a vector in Rn. If we are using cosine similarity, and we are in Df IDF space, then we are interested into computing all similarities between the documents in our corpus, which are the columns of X, and the new document or query Q, and the similarities can be computed by computing X transpose Q, okay, which is the matrix by vector multiplication, so that Q is multiplied by every document in X, meaning every row in X transpose. But this can also be done as V sigma Q transpose Q by the definition. This is not necessarily what we want, this is just an equality, but it turns out that we can choose an R prime smaller than R. We can define sign matrix approximations by removing, for example, removing from Q by keeping only the first R prime columns of U, the first R prime columns of V, and the first R prime eigenvectors of sigma. What we obtain is that we are making these matrices smaller by taking away the parts of the matrices that provide the smaller contributions to the matrix X, because they are multiplied by small singular values here. So the idea is that if we took this smaller R prime, possibly much smaller, we will be able to compute an approximation to these similarities. So, an approximation to X transpose Q by using these truncated matrices. And in particular, we can see this operation, this operation, as composed of two steps. In the first step, we are defining a new query vector by transforming our original query vector Q into a much smaller vector. We go from size n to size r prime. So this is a sort of projection onto a more suitable space where our query becomes much shorter, so that the similarity that we want to compute can be given by V r prime sigma r prime q r prime. Okay, the idea is that if in the original space the matrix that provides the similarities is X transpose, in the new space where we have a much reduced set of dimensions, our similarity matrix, the matrix that provides similarities, is Vr prime sigma r prime. And coordinates are much reduced. Okay, this is a synthesis of what we have seen yesterday. Now, computing the singular value decomposition can be rather tricky, because we need to take into account many details when we determine the matrices U and V. So today we will just have a rapid look at how things work by using the R package with which already has a singular value decomposition function, just to see what it looks like. Okay. Okay, so this is simply the how to deactivate the audio. So in this script, I'm just going to define a matrix. Well, actually, here the matrix was called A, not X, but I think it's the only variation because I took this from last year's exercises where probably I used a different notation. Anyway, we have set of 6 documents in 5 dimensions. In this case, here I'm defining matrix A as this set of 6 columns, each having 5 values. Okay, at the end, 5 rows and 6 columns. Well, let's just see the output, because the output also contains the command lines, so we can see it simply. So first, we define matrix A. And of course, we can just print A and verify that what I defined at every row up there ends up like a column in the final matrix. Next, suppose that I want to find all pairwise similarities between documents. In this case, the matrix containing all pairwise similarities between documents is A transpose A. Okay. Every row of A transpose dot multiplied by every column of A. What we get is this document similarity matrix. Okay, similarity between document 1 and itself, between document 1 and document 2. Of course, the matrix is symmetric, because that product is symmetric, and so on, just to have a look at some numbers. Next, okay, I just have the function SVD that computes the singular value decomposition of matrix A. The singular value decomposition contains a set is returned as an object, which I will call SVD, and here I take the different members of this object according to the R syntax. So, for example, matrix U in object SVD is obtained with syntax SVD $U. Okay, so here you have the 3 matrices that compose A. So this is a matrix U, this is matrix V. Nothing to say, just random number as far as I can see. And this is the diagonal matrix with the singular values. The singular values were already provided in decreasing order, as you can see. Actually, they were returned, you can see here, they were returned as a vector, but with the function diag, you get easily the diagonal matrix with a vector. So we have the singular value decomposition of A. Now we can make a few checks to see if the R definition of singular value decomposition is the same that we want, but in fact, if you check the column orthonormality of U by multiplying, this is the syntax for U transpose U, and in fact you get the identity matrix. You see, elements in the diagonal are exactly 1, elements outside the diagonal are 0 for all practical purposes, apart from numeric errors, of course. Same for V transpose V. And finally, we can see that if we multiply U by sigma by V transpose, we obtain the same matrix we started from. So this is the SVD decomposition as we defined it. Okay, now let us define a new document, a query. Of course, it will be a 5-dimensional vector because all our documents are in 5 dimensions. The first question we can ask, independent of the SVD decomposition, is what is the similarity between our new query Q and all the document in matrix A? We know that we just have to compute A transpose Q, and we get the list of the vector of all similarities. So we know that the similarity between document 1 in our corpus and the query Q is 56, and so on. In particular, document 6 is the most similar. Okay. Now, let's try the same, but by moving to the SVD decomposition. Oh, here I have an error. Yes. So, let's see the first line here. As I told you before, using the SVD decomposition means, okay, take your original query Q and project it using U transpose into a new space. This is what I have done, and this is the same query in the, let's call it the SVD space. Now the similarity can be computed by multiplying V sigma times this vector. Actually here I forgot to put sigma. I need to add it now. Okay. This should be it. Okay. So this is the original. So this is the original query with the original similarities computed directly by multiplying the matrix. This is the transformed query in SVD space. If we multiply it by V sigma, we get exactly the same values. Okay. That's what is expected because we just multiplied V times sigma times U transpose by Q. And we know, we already checked that V times sigma times U transpose is A transpose. So, nothing new. Now, we move to the actual latent semantics indexing part. So, we have seen that the SVD works. Now, let's reduce the rank of the matrix by removing the smaller singular values, and let's see what approximation we get. So here, everything everything until our last computations had a rank equal to 5. We had 6 documents with 5 dimensions. You know that the rank is at the most the smallest between the two. And in this case, we had full rank, so the rank was 5. How could we see that the rank was full? Because all singular values were different from 0. The idea is that the dimension of S, removing possible zeros at the end, is actually the rank of our matrix. So now we reduce the rank. How do we reduce the rank? So suppose that we want to reduce the rank to 3. Okay, we take every matrix. So we take matrices U, V, and sigma. We only keep the first k columns in U and V. We redefine sigma key as the diagonal of the first k singular values. Here I also defined the inverse, but we don't need it. So now we are working with matrices UK, DK, and SK, sigma k, that are smaller than before because we removed the 2 columns from each. And the rank, which is the size of sigma, is reduced to 3. And in fact, if see here, I define AK as the product of these matrices, so that AK is the actual approximation of A. We actually don't need to compute AK. The whole purpose of this method is to never go back to A to make computations. So we don't need to compute it. But just to see how it changed, let me print it. So after defining this, after defining AK, let's print it. Oh, actually, it was printed down here, but okay. Okay, this was the original A. Okay, AK is up here. For example, if you remember, the first column was 1, 2, 3, 4, 5. Now it has become, slightly more than 1, slightly less than 2, slightly less than 3, and so on. This is an approximation. A rank 3 approximation. It means that now not all 5 rows of this matrix are linearly independent. This matrix contains less information than the original one. Okay, this is the important part. And we don't really need this matrix. It was just to see it. What we actually need to do to compute similarities is up here. First, we take our query Q and we project it to the reduced LSI space by multiplying it by UK transpose, obtaining a vector of 3 elements. Now we are in R3, which is of course made by the first 3 elements of the previous transformation of Q. Next, yes. I was printing too many things. And here I forgot again to multiply by sk. Okay, it's vk, sk, qk. Okay, once we have this, and we multiply it by this matrix, which is, again, smaller than the original one, we get some approximate similarities that resemble the real ones. Maybe I can also rewrite the similarities. So that we can compare. Okay, these are the true similarities in the original space, in the TF-IDF space. These are the approximate similarities in the LSI space. So in the reduced rank with the rank reduction. These approximate similarities, as I told you yesterday, require much less computations when we are dealing with large matrices and we are making drastic reductions to the rank, and also tend to be more faithful to the document semantics somehow, because they represent the removal of small effects represented by the smallest singular vectors, the singular values, which are most possibly just noise. Anyway, you see that in this case the approximation is good enough, and not only when we compute similarities, we are not interested in the actual similarity value. We use the similarities to rank documents. So we only want to see which document it has the highest similarity, in this case, the last. So even if there are strong variations, as long as they don't overlap each other, the result is exactly the same. Please.
So the input Q is more similar to the document number 6.
Exactly. And also, from both points of view, our input document, the most similar document in our collection, that is to Q, is 6, right? And in this particular case, the ranking remains exactly the same in the two cases. Of course, as I said yesterday, the real numbers are usually much larger. Okay. Actually, I thought a little about what you asked yesterday about interpreting the reduced rank dimensions as topics, which is okay, but see, usually when we speak of topics, we mean that the document has one topic. So the term topic tends to be exclusive. If the document is about programming, it's not about sports. In this case, actually the opposite is true. Because with this technique, we find directions that are independent of each other. And independent is somehow the opposite of mutually exclusive. What we get here is that the topic directions are not correlated. So we can measure independently if the document is, well, the fact that a document follows one of the topics in the LSI space does not influence the probability that the document follows another topic, because in fact, it all descends from the fact that the covariance matrix is diagonal. Okay, so it's true that we are identifying a smaller number of topics for our documents. There are not more topics in the usual sense because they are not mutually exclusive. Every document is a combination of these topics where every topic is treated independently of the others. I don't know if it's very clear. Okay. Yes, what I mean is suppose that you have two documents which are programming and politics. Suppose that there are no politically oriented languages. This is not strictly true, but assume that it's so. Of course, if some document is high in the topic of programming, it will be probably low in the topic of politics. So either document is about programming or it's about politics. So we expect our clouds to be sort of like this. What we get from this system is something where the cloud is perfectly uniform with respect to the coordinates. So it's something different from what we expect from actual topics. Okay, so in the next page, maybe I will also put this on the web page, and maybe I will slightly change the names of the variables so that they reflect what we have seen in theory. For example, I will call the matrix X instead of A, and so on. So now maybe we could have a look at one exercise about it, something that you could find in the written exam. We're asking so.
In this case, it seems like the similarity measures are somehow the same.
Yes.
Even if you reduced it. So the relevance of reducing it for this case
well, no, actually this was built in order to precisely make my point, which was we obtain very similar results with much less calculations. In fact, what we have here is that all the multiplications that are involved are on much less dimensions. In this case, okay, not much less, 3 instead of 5. So my point is simply that this is similar to this, but this was obtained with 3/5 of the multiplications. Okay. Of course, we can also make another test. We can simply reduce k to 2, so make it slightly smaller, and see what happens to, well, it looks maybe even more similar. Well, okay, even reducing the rank to 2, we get something that is still good, maybe even better than 3. Let's go to 1. Okay, rank 1 means we are throwing away almost all information. We have that all rows and all columns in our matrix are linearly dependent. So we are really losing a lot of information. Oh. Yes. Oh. Okay, we have a syntactic problem here. So I would need to change a little the script, because if you cut away just one column of a matrix, then R interprets it as a vector and does not work anymore as expected, as you can see. And in particular, the diagonal matrix here, which should have only one element, it became actually a 16 by 16 matrix. I don't know by virtue of which effect. Okay, so let's not consider the rank 1 case. Anyway, even if you reduce everything to rank 2, with less computations we get similar results. Okay, so actually we projected our original query with, which was from 5 dimensions, into 2-dimensional queries by only keeping the 2 most important dimensions in our SVD space. Okay, questions? Okay, now let's see some possible exercise. So I still didn't put them on the among the exercise of the exercises of this year, because I needed to change a few things before having it. I will put it on the website in the next days. So, for example, Suppose that we have our document matrix, which is like this. Okay, actually here we have, I've taken out a multiplier which should multiply all numbers. I just collected this 1 divided by square root of 6 here, because this will help us have deal with integer numbers in the rest of the exercise. So it's take it as a normalization factor. So this is a matrix of 3 elements, of 3 documents. Please.
So 2 documents are equal.
2 documents are equal. Yes. Yes, this is a matrix that lists 3 documents in a 4-dimensional DF-IDF space. And in fact, the first question is, okay, what is the rank of matrix A? So actually having 2 equal documents was to make that answer as easy as possible. Okay. So first question, what is the rank of matrix, X? And of course, we know that the rank can be at most 3, but 2 columns are equal, so at least 1 column is not linearly independent, so the rank can be at most 2. But if you focus on these 2 rows, you see that they are not proportional to each other, which is the only possible way to have 2 linearly independent columns. So the rank of our matrix is actually 2. Okay, so the first question was just about understanding what the rank of a matrix is. The second question, okay, we have a query Q, 1, 3, 0, minus 2. And the second question is compute the similarities between all documents in our collection and the new document Q. Where the similarities are the ones given by the dot product. So we're speaking of cosine similarities. So simply similarities are the dot product between the columns of X and Q. So we can write them as X transpose Q. X transpose Q, which is, okay, let's keep it 1 divided by square root of 6 outside. So let's keep 1 divided by square root of 6 collected outside. So we just need to compute this dot product. It's 2 minus 4. Okay, so minus 2. The second is 3 plus 2, so it's 5, I think. And of course the third column is equal to the first column, so we're writing out the similarity. Okay, so the answer to the second question is just this. The third question, I actually need to remove the screensaver. Okay, the third question is, we have a matrix so let matrix U be some coefficient alpha times 1, 0, 1, 1 and 0, 1, 1, minus 1. And let V be the matrix 1, 0, 1 and 0, 1, 0. V is 1 divided by square root of 2 times this. And the question is, determine alpha, this alpha, and a diagonal matrix, a diagonal positive matrix sigma, such that U and V are column orthonormal, and the original matrix X is U sigma V transpose. This is it. Okay, so in this case, I'm just providing most of the pieces that we need to compute the singular value decomposition of our matrix. What we are actually missing is this coefficient and then the singular values. Of course, the singular values in this case are 2 because the rank of the matrix is 2. So what we have to determine is okay, we know that sigma is actually sigma 1, 0, 0, sigma 2. So we're asked for these 3 numbers. The first one that we can determine is, of course, alpha. Alpha must be computed so that U is column orthonormal. In particular, it means that the dot product of a column of U by itself must be 1. Or, more simple, if you prefer, let's compute U transpose U. U transpose U is, okay, we collect alpha from both, then we have here 3 0, 0, 3. And we want this to be equal to 1, 0, 0, 1. So of course, alpha must be 1 divided by the square root of 3. Okay, alpha square must be 1/3. So alpha is 1 divided by the square root of 3. So actually, to compute alpha, given that we were already assured that U could be column orthonormal, we only need to compute the dot product of the first column by itself. So we would find alpha. Okay. Next. Oh no. Sorry, we are still missing this. So how do we compute sigma 1 and sigma 2? Well, we can just write down the equations. So we want our original matrix X to be equal to U sigma B transpose. So to be equal to alpha, which is 1 divided by square root of 3, times 1, 0, 1, 1, 0, 1, 1 minus 1. Times sigma 1, 0, 0, sigma 2, times B transpose, which is 1 divided by square root of 2, 1, 0, 1, 0, 1, 0. Okay. This is, we want this to be equal to x, where x is 1 divided by square root of 6, 2, 0, 2, 2, 0, 1, 1, minus 1, 2, 0, 2. Okay. We want to find sigma 1 and sigma 2 so that this equality holds. In this case, we can throw away square root of 3 and square root of 2, which simplifies with square root of 6. And then we need to compute this product. But actually, we don't need to compute every product. We just need to compute one product that contains sigma 1 and one product that contains sigma 2. For example, well, let's multiply. So let's start by multiplying sigma times B transpose. So we have this product becomes sigma 1, 0, sigma 1, 0, sigma 2, 0. Multiplying on the left by diagonal matrix means you multiply every row of the matrix by a different value. This is 1, 0, 0, 1, 1, 1, 1, minus 1. So finally, this product multiplied by this matrix is course it's going to be a 4 by 3 matrix. Let's just compute the first element, which is sigma 1 times 1 plus 0 times 0, so it's sigma 1. But then maybe we compute something that contains a sigma 2, for example, the second row by the second column, that gives sigma 2. We can also leave indeterminate all other numbers, because now we know that if this matrix must be equal to this, then sigma 1 must be 2 and sigma 2 must be 1. Okay. I mean, if we want that this product of matrices is equal to this matrix, we just need to compute as many elements as needed to define all the unknown values, which in this case are sigma 1 and sigma 2. So at last we have sigma 1 equal to 2 and sigma 2 equal to 1. So we have the full singular value decomposition of our matrix. So U is 1 divided by square root of 3 times its matrix. B was already given. Sigma is 2, 0, 0, 1. The next question, let me retrieve it. Okay, fourth question. Once we have this decomposition, so the fourth question was, given that now we have the singular value decomposition, and given I erased the query, which was 130 minus 2. Here, our query is 130 minus 2. The next question was, okay, project Q onto the SVD space and compute the same similarities as in point 2. So to project the Q on the SVD space, let's call it Q prime. We know that we have to compute the U transpose Q. Which is 1 over square root of 3. U transpose is 0, 1, 1, minus 1, and 1, 0, 1, 1 times 1, 3, 0, minus 2. So we get 1 over square root of 3 times 3 plus 2, 5. And 1 minus 2, which is minus 1. Okay, our work let's say, the query has been simplified. Initially, it was a 4-dimensional document in the original TF-IDF space, but our matrix had rank 2. So actually, all the information from the query we need to compute similarities is this 2-dimensional information. We moved actually to a lower dimensional space. And now we know that in order to compute a vector of similarities, we have to multiply V times sigma times our new vector Q prime. Now, but let's write it explicitly. V is 1 over square root of 2 of 1, 0, 0, 1, 1, 0. Sigma is 2, 0, 0, 1. Our query Q is 1 over square root of 3 times 5 minus 1. Okay, I can collect together the two coefficients. This becomes 1 over square root of 6. Multiplying sigma by, well, now let's multiply, sorry, here was an error. This is 1, 0. This?
You transpose it also.
You transpose here. No, this is, let me have a, yes, no, here I need to transpose.
The
Yes.
value is not correct.
Oh, really? I see.
Yeah.
Oh, I swapped the two. Well, okay. So it's easy to correct. This is a very strange error, actually. Well, let's check it again anyway. 1 minus 2 and 3 plus 2. Okay. So this should be the final result. So also here, minus 1 and 5. Okay, now we can compute V times sigma, which is simply this row. So the first column is multiplied by 2 and the second is multiplied by 1. So we can incorporate this sigma just by multiplying by 2. This. So here we have the query in the SVD space and the similarity matrix, the matrix well actually the matrix that we need to multiply it by to get similarities. In fact, if we do the multiplication, we get 1 over square root of 6 times and 3 values, minus 2 times 0, 5 and minus 2. which is exactly the similarity that we had before when we computed it directly in the original space. The main idea was that originally we had a 4 by 3 matrix and a 4-dimensional query, while here we have a 3 by 2 matrix and a 2-dimensional query, just to have exactly the same result. We removed everything. We maintained all information with a much smaller, number of entries. Okay, this was just a question to check that the results are exactly the same. The next question, the final question was, suppose now that we want to reduce the rank to 1. Okay, we already know that the rank of the matrix is 2. What happens if we sacrifice one of the singular values, the smallest one, of course? What changes in the similarities? So we now have to do exactly the same calculations of 0.4, but with rank 1. So by actually removing pieces from our matrices. Of course, rank 1 is not realistic in applications, but it's just to see what happens by hand. So we are actually removing the lower right border of matrix sigma, which becomes a 1 by 1 matrix with value 2. And we are equivalently removing all columns, with the exception of the first, from matrices U and V. Now, of course, computations become even easier than before, because the new approximation of Q, let's call it QK, which is UK transpose Q, is now a single value. Okay, the size of the query in the restricted space, in the LSI and the SVD space, is the rank. Now, if the rank is 1, in fact, we are multiplying this single column matrix by Q. So we get 1 divided by square root of 3 times this column by this vector. I don't remember how it was before. 1 minus 2, so it is this very small vector. Now, of course, the approximate similarity vector, so given by approximate with rank 1, which is Vk sigma k Qk, okay, it's just, okay, as before, we have 1 over square root of 2 times this column matrix 1, 0, 1 times sigma k, which is just 2 times our query, which is 1 over square root of 3 times minus 1. So the approximate similarity is 1 over square root of 6 times minus 2, 0, minus 2. Okay. See, in this case, we have lost a lot of information. But actually, similarities are somehow still in the correct order because, well, the first and the last are negative, the other, okay, it's no more positive, but it's anyway greater. Of course, this reduction means that, you see, we are actually, if the query is reduced to one value, it means that we are forgetting everything about the query. What we are interested in is actually, so we are reducing everything to one topic, so there is no meaning in this. Anyway, it was just to see how the computations are carried out.
Sorry. When we reduce to one topic, we say that every document belongs to a single topic, or we are saying that we think, I mean, which topic we choose? The first one.
The most representative one, the one that in the SVD sense gives the largest, has the largest variability. Remember how the matrices are obtained, okay, by first of all isolating the direction where we have the largest covariance. The largest exactly. So here we are only keeping the topic that shows the most variability of our data. But of course, we are losing almost all information because here we are actually saying that our system is just described by one feature. Having machine learning with one feature is useless. Okay. Oh, let's see. I have. It's a little late, but I can start with another exercise so we can at least discuss a little, and then I will put it on the net and we'll see it better next, well, Monday or Tuesday. let's consider a singular value decomposition again. In this case, we are told that we have a matrix X that can be expressed. We have a matrix X whose singular value decomposition is the following, where U is 1 over square root of 2 times 1 minus 1, 0. Sigma is 3, 2, 1. And B is okay, so in this case, we know that this is valid SVD of our matrix. So the exercise, the text itself of the exercise tells us that this is a correct SVD. So we don't need to check it. Maybe if you check it, you also find some error. So maybe we need to check it. But for the sake of the exercise, let's suppose that this is the SVD. The first question is, what is the rank of matrix X? And the answer is immediate. Please. Okay, somebody has proposed a 3. Why? Well, simply, if this is a valid SVD, then the rank is given by the non-zero entries in this diagram. So, the fact that this is an SVD already means that U and V are column orthonormal. Being column orthonormal, we are sure that they are the columns are linearly independent. So the rank of U and V is always full. So the number of non-zero singular values is the rank of the matrix. So we are sure that the rank of the matrix is 3. And the second question is, okay, now reduce the rank of X by 1 dimension. So we want an approximation with only 2 with rank 2. So the only thing we need to do is remove the smallest singular value, so that sigma becomes a 2 by 2 matrix. Let's call it sigma 2. U, let's call it U2. Only keeps 2 columns. Also V, V2 only keeps 2 columns. Okay, question 2. Reduce the rank is just a matter of cutting away a few things. Now, what's left is the material by which and rank 2 approximation of the original matrix can be obtained. Next question. Well, next question is rather long. It asks, okay, given this approximation of matrix X, let's apply an agglomerative clustering procedure to the documents. Oh, by the way, how many documents are there? 2, 3, 4, 10, 1,000. So what's either in the original decomposition or in the rank 2 reduction, what is the what in that decomposition gives you the number of documents in the set? Any idea? Remember that the number of documents is the number of columns of matrix X. So it's the number of columns of V transpose. So the number of rows of V. Okay. So we are dealing with a document set with 4 documents in a 3-dimensional DFIDF space. In fact, it might as well have been the first question. Okay. So given that X is the representation of column document vectors, we have 4 documents in 3 dimensions. Okay, so the third question was perform a hierarchical clustering on the data set, of course, of the document set. You know that in order to perform hierarchical clustering, all that we need are the similarities between documents. So I'm explicitly asking to perform this procedure where similarities are given by the rank 2 approximation. Of X. So even before performing this clustering, we need to compute these similarities. So the 2 approximation, the rank 2 approximation of X is of course U2 sigma 2 V transpose 2. Okay. it's exactly X where we removed all the low information part. The part with little information content. Here, we don't need to explicitly compute this matrix, because all that we need is the matrix with approximate similarities, which is, as we know, x2 transpose x2. This is the matrix that we actually need. But x2 transpose x2 is b2 transpose sigma 2 u2. No, sorry. b2 sigma 2 u2 transpose u2 sigma 2 b2 transpose. But we know that the first two columns of u are orthonormal, so this is the identity. So it's b2 sigma 2 squared b2 transpose. And this is what we need to compute to have all pairwise similarities between documents. So it's just a matter of placing the numbers, which are 1 over square root of 3 times 1, 0, 1, 1, 0, 1, 1 minus 1 times sigma 2 squared is 9, 0, 0, 2 times 1 over square root of 3 and the transpose of B2, which is 1, 1, 0, 1, 0, 1, 1 minus 1. Okay, this is what will give at last similarities. Of course, 1 over square root of 3 times 1 over square root of 3 is 1/3. So the product between these two gives 9 times the first column and 2 times the second column. So finally we have, let's write it here, it's 1/3 times, of course we have 4 documents, so we are having a 4x4 matrix. So this should be the final similarity matrix, and of course one check that you have to do is that it should be symmetric. So once we have computed this approximate similarity matrix, we can start with the clustering procedure. Of course, of all the numbers that we have here, for the clustering procedure, we only need a subset. The numbers here in the green frame already give us all the similarities that we need. We don't need the similarities between one document and itself. So if we call documents 1, 2, 3, and 4, the largest similarities of the first two documents that we should merge in the same clusters are either 1 and 2 or 1 and 4. No, so, oh, okay. There was a similarity of 11, but it was between the document and itself, so we're not interested in it. So our first step will be merging, for example, documents 1 and 2 together at a similarity level equal to, well, actually it's 9/3, because we also have a 1/3 coefficient here outside. And as you know, after we have merged two elements together, we need to compute the similarities between the newly created cluster and the remaining documents, which of course depends on how we define the set similarities, as we have seen some time ago. And I don't remember which definition I was giving here. Oh. Okay. Here, for example, I was asking to define the similarity between clusters as the self-similarity measure. Self-similarity means put together the two clusters and compute the average similarity of all pairs, which actually takes time. So suppose that we define the similarity as the largest similarity between documents in the two sets. So the similarity between, let's say, cluster 1 and cluster 2 is the largest similarity by taking an element in cluster 1, an element in cluster 2, so that in order to proceed, we have to compute the similarity between the cluster 1, 2 and the elements 3 and 4. Then of course, so the similarity between 1, 2 and 3 is the largest between the similarities of 1, 3 and the similarities of 2, 3. 1 and 3 are 0, 2 and 3 are 2, so this similarity is 2. The similarity between the cluster 1, 2 and document 4 is the largest between the similarity between 1 and 4 and the similarity between 2 and 4, which is 9. What's left out is the similarity between 3 and 4, which is -2. So in the next step, we're going to merge elements 1 and 2 with, so the cluster 1, 2 with the element 4, and again at the same similarity level actually. 9/3. And of course, the similarity now between the cluster 1, 2, 4 and the singleton 3 is the largest between the similarities between 1, 2 and 3 and the similarity between 4 and 3, so it's 2. So now 3 can join everything in a common cluster at 2/3 similarity. And this is the resulting diagram. Okay, anyway, I'm going to put those exercises on the network so you can have a look at them. And maybe if you have questions next time, we can discuss them. Okay, I think that's all.